Swayam Prabha. Digital India. Educated India.
Vertical alignment part 1. We have already discussed about horizontal alignment. Today we shall start our discussion about vertical alignment. After completing this lesson, the student will be able to understand different types of gradient used for design of vertical alignment, appreciate the need and understand the basis or the procedure for applying grade compensation, and also student will be able to design summit curves and valley curves following Indian Roads Congress approach or guidelines. Natural ground may have slopes or undulations of various magnitudes. We do not expect the ground to be perfectly flat, so it is expected that there will be undulations. Vertical alignment basically should provide for a smooth profile consistent with the general topography. It cannot be in absolute terms, like it depends on the terrain. For flat or say for plain terrain, whatever alignment is possible, it is difficult or maybe economically not viable to attempt to provide that kind of vertical profile for hilly region. So, it has to be a function of the terrain. Vertical alignment includes tangent and curves, but in this case tangents are essentially grades and curves are vertical curves. There are several influencing factors which control the overall vertical profile design. Say there are a large number of factors, to mention a few: vehicle speed, side distance consideration, comfortable acceleration deceleration characteristics and other features. Now, we have already discussed earlier about the topography classification. Indian Roads Congress use 4 types of terrain classification, namely plain terrain, rolling terrain, mountainous and steep terrain, and the terrain is classified based on the percentage of cross slope, that is slope approximately perpendicular approximately in the perpendicular direction of the road. That is what is normally indicated as cross slope. So, depending on the cross slope, 4 different terrains are defined. Similarly, AASHTO they define 3 types of terrain: level terrain, rolling terrain and mountainous terrain. This terrain classification is relevant because we know that the vertical profile also will depend on the terrain condition. It is not possible to achieve the same standard at all terrain conditions. There has to be compromise in terms of when the terrain condition is difficult. Now, let us see different categories of gradient what are used in Indian context. IRC defines mainly 3 types of gradient. Of course, there is one lower limit also. So, if we consider them that way, there are 4 types of terrain. First is the ruling terrain. Now, ruling terrain is generally what we should try to use for normal design practice. That means, this is the limit what we should try to use as far as possible under normal condition when we are adopting the design. So, it is basically generally used in design. So, they are generally called as also design gradient. It is not an easy task to fix the limit for ruling gradient, because the gradient whatever is acceptable in a plain region may be the same type of gradient may not be acceptable for a hilly region. So, it has to be a function of the terrain classification, or depending on the terrain condition it will vary. Similarly, length of the grade and speed. Now, when vehicle negotiate grade, depending on what is the grade, there will be actually loss in speed. Longer the length of tangent and higher the grade, there will be higher reduction in speed, which is again which is likely to influence the overall traffic operation. So, therefore, length of the grade also is another factor. We cannot simply say this is the limit or this is the value of the ruling gradient, but also what is the length, that also is important, what is the speed of vehicle, that is important, and then this reduction or the loss of speed depends on the pulling power of vehicles. So, pulling power of vehicle will also control that for a given grade what will be the to what level the speed reduction is possible. Then the vehicle operation is also affected by the presence of horizontal curves. That means, in addition to gradient, whenever horizontal curves are there, there are additional losses or additional resistance. All these things make it a complicated task to fix up the limiting value. Also, for Indian condition, the traffic environment is heterogeneous or the mixed traffic environment. So, therefore, different vehicles have different speed capability, different pulling power. Okay. So, altogether it becomes a very, very complex task to suggest or to decide a single value for ruling gradient. Next is limiting gradient. This gives you another limit, and obviously this is steeper than the ruling gradient. Depending on the topography, it may not be possible to provide or to limit the gradient up to ruling gradient. Let me revise this statement. It might be possible to achieve that gradient or to keep it or to limit it up to the ruling gradient, but maybe with increase in cost, which is substantial, and it may not be economical also to try to achieve that. So, therefore, depending on the topography and also considering the cost, there is another upper limit where acceptable gradients are bit steeper than the ruling gradient, and that is what we call as limiting gradient. Now, obviously, since limiting gradient is steeper than ruling gradient, length of continuous grade line steeper than ruling value should be limited. Then the third type of gradient, what is used, that is exceptional gradient. It is further steeper than the limiting gradient, and by name itself it is exceptional. So, it will be used or applied or accepted only under exceptional condition. Complex situation, terrain condition does not permit. If we try to provide a flatter gradient, cost is going to be enormously higher. So, under truly exceptional situation, one can adopt exceptional gradient. So, that is another limit which is also given in IRC. But since exceptional gradients are much steeper, we should not use exceptional gradient for a continuous length of the stretch. It can be used only for short stretch, normally not exceeding about 100 meter at a stretch. Normally not exceeding 100 meter at a stretch. So, only for short length it is permissible. Now, it depends on gradient, depends on terrain condition, and there are three types of gradient: ruling gradient, limiting gradient, exceptional gradient. So, this table shows that for plain terrain, for mountainous terrain, for steeper terrain, what are the values. Now, obviously, ruling to limiting to exceptional values will gradually become higher. Values will gradually become higher. Say for example, for plain and ruling terrain, ruling gradient is 3.3%, limiting gradient is 5%, exceptional gradient is 6.7%. So, you can say 5% is higher than 3.3, again 6.7 is higher than 5%. Similarly, as the terrain becomes difficult, this way vertically also the values will increase. So, for ruling gradient in plain terrain, the limit is 3.3%, mountainous 5%, and for steep terrain it is 6%. Like that, for different terrain condition, the limiting values of ruling gradient, limiting gradient and exceptional gradients are given. Now, there is also another type of gradient which is called minimum gradient. Now, let us first try to appreciate the need for minimum gradient. Camber will normally help the water to disperse and go to the side drains. Then again water has to flow in the side drains. So, actually a mild longitudinal slope is required along the length of the side drains. Say if we consider even a mild slope, say 1 in 300, which is generally mild slope, then that means for a length of 1 kilometer, we need the downstream to be depending by 3.3 meter as compared to the upstream. That means in 1 kilometer length, you need basically 3.3 meter depending of downstream. Is it practical? Probably the answer is no. It is extremely difficult to maintain that kind of gradient by earthwork. So, the idea is if we can provide a natural slope, obviously where the terrain condition permits, if we can provide a mild longitudinal slope, that itself will solve this kind of problem. That means obviously the side drains also the water can flow without any problem. So, a certain longitudinal slope is desirable to drain the water along the side drain, and obviously this is possible or should be attempted if topography favors. So, matching it to the natural topography, if we can provide a mild longitudinal slope, that may be beneficial. Obviously, how much gradient is required, that will depend on the rainfall, runoff, type of soil and the topography. So, gradient may vary in general, say 1 in 500 for concrete drains to 1 in 100 for kacha drain. Obviously, for concrete drain we need a milder slope is acceptable, but for kacha drain or earthen drains you need a much steeper slope. Now, grade compensation. This is another topic itself. What is grade compensation? When there is a horizontal curve in addition to gradient, there will be more resistance due to both gradient and the curve. This is often a situation what we encounter in hilly terrain. We have gradient and we also have horizontal curves. Now, why there will be additional resistance? We also discussed earlier about the curve resistance, but let us again try to refresh our memory. Suppose if this is the tractive force which is available in the direction of movement, and if the vehicle is negotiating a horizontal curve, then this T alpha, T cos alpha component, if this angle is alpha, is only available in the direction of movement, because rear axle this tractive force is there T. In the direction of movement, front wheels are rotated in this direction, making an angle alpha. So, therefore, in the direction of movement T cos alpha is available. So, not the T complete T is available. Now, if there is a gradient also, say let us call another angle beta. So, then again T cos alpha cos beta, that component will be available in the direction of the movement. So, there will be additional loss. In the curve resistance, the loss is T into 1 minus cos alpha. Similarly, due to the gradient also, there will be additional loss depending on this angle. And now, this angle will obviously be more when the grade is more or a steeper grade is used. Therefore, to avoid this excessive loss which will affect the vehicle movement as well as which will affect the overall traffic operation on roads, it is necessary to go for grade compensation. That means, compensate in terms of grade, that is provide a lesser grade than what is normally used when there is no horizontal curve. That means, if we provide if horizontal curve is encountered, compensate in terms of the gradient, so that the overall operation remains acceptable. So, it is reduction in gradient in horizontal curve to keep the total resistance within acceptable limit. IRC suggests this basis for grade compensation. So, grade compensation is basically 30 R by 30 plus R by R, where R is the radius of the curve. So, that amount of grade compensation may be applied. Now, when we are applying this, there is also a maximum limit which is suggested in the code. Maximum value of grade compensation is 75 by R. So, when we are doing grade compensation using this basis, we have to also check whether the value exceeds 75 by R. If it exceeds, then the maximum value to be provided as 75 by R. Also, grade compensation is not necessary for grades less than 4%. So, if the initial grade is less than 4%, there is no need of providing grade compensation. Also, if we are initial grade is steeper than 4% and we are going for grade compensation, then we need not use the grade, below 4% when we are compensating the grades, because anyhow if it is less than 4%, we need not go for grade compensation. So, when we are calculating the compensated grade, if the calculation becomes theoretical calculation shows a grade less than 4%, we can only go up to 4%. So, it need not be eased below 4% gradient. That is the grade compensation part. Let us take an example problem. In a hill road section, say the ruling gradient is 6%, radius of horizontal curve is 65 meter, then we have to calculate the compensated grade. Now, grade compensation as per the earlier discussion, it is 30 plus r by r. So, r is the radius of curve in meter. Here the radius of curve is 65. So, we put this value 65. We calculate the grade compensation as 1.46. But we also need to check the maximum limit. So, maximum limit of grade compensation is 75 by r. So, 75 by 65, which is 1.15 percentage. Now, this grade compensation whatever we have calculated, it is 1.46, which is higher than 1.15, which is the upper limit, that is 75 by r. Therefore, we provide grade compensation only up to 1.15%, not up to 1.46. So, accordingly we calculate the compensated grade. 6% was the initial grade, here it was indicated, minus this 1.15%. So, 4.85%, and 4.85% again is more than 4%. So, therefore, it is acceptable and it is okay for design purpose. So, the compensated grade is actually 4.85%.